Figure below shows a Carnot cycle. Plot the Carnot cycle in the graph of temperature versus entropy, T versus S. The graph given in the figures is the P versus V graph, where the P is pressure in Pascal, V is volume in meter cubes. There are 4 states indicated in the graph: state 1, state 2, state 3, and state 4. From state 1 to state 2, this is the isothermal process. So this graph requires the isotherms. From state 3 to state 4, this is also an isotherms. But from 1 to 2, this is isothermal expansion process. And from 3 to 4, this is isothermal compressions. From state 2 to state 3, this is adiabatic, and the graph requires the adiabats. And from 2 to 3, this is the adiabatic expansions. From 4 to 3, this is the adiabatic compressions. So these two curve is the adiabats. Now in these questions, we need to plot this Carnot cycle in the graph of temperature versus entropy. So this T is the temperature, the capital S is the entropy. We want to transform this Carnot cycle into the graph of the T versus S. So we need to know what is the relationship between the temperature and the entropy. We have this entropy change formula, which is equal to Q over T, where the T is a constant temperature. Q is a heat transfer to the system or from the system. So that means to plot the graph of the temperature versus entropy for the Carnot cycle, for this Carnot cycle, we need to know for each process how the Q change and how the temperature change in these 4 processes in that form the Carnot cycle. We now start to analyze the process for the change of the state from 1 to 2, this which is the isothermal process. Now if this is isothermal process, then the temperature change is equal to 0. That means the state 1 and state 2, they have the same temperature. Now if this temperature change is equal to 0, that means in this process there is no change of the internal energy. Delta ETH is the change of internal energy, and it must be equal to 0 because internal energy depends on the temperature T. And from 1 to 2, this is the isothermal expansions. When the gas expands, the work done by the gas will take the positive value. So W larger than 0. And based on the first law of thermodynamics, we know that it is Q equal to internal energy change plus the W. Therefore, since this internal energy change is 0 and the W is larger than 0, we know that the Q in this process, when the state change from 1 to 2, the heat Q is larger than 0, means that the heat is absorbed by the gas in the process 1 to 2. From state 2 to state 3, through the adiabatic process, the temperature of the gas drop from state 2 to state 3. That means the temperature T2 is larger than the temperature T3. Because this state 2 is lies on these isotherms and state 3 is lie on this isotherm. And this isotherm is located to the right compared to this isotherm. Therefore, the temperature T3 must be less than the temperature of the T2. So delta T less than 0. And from 2 to 3, the process is the adiabatic expansion. So for any adiabatic process, the Q is equal to 0. That means there is no heat transfer happens in this process from 2 to 3. From state 3 to state 4, this is isothermal compressions. Since it is isothermal, that means there is no change in the temperature, delta T equal to 0. Therefore, the internal energy change also equal to 0. Work done is negative because from state 3 to state 4, it involves the compressions of the gas. So when the gas compressed, the work done by the gas is a negative value. Again, from the first law of thermodynamics, where the Q equal to internal energy change plus work done. Since this is 0 and work done is negative value, therefore the Q in the process of from 3 to 4 must be less than 0. So in this process, the heat is leaving the gas in the Carnot engine. For the last process in the complete Carnot cycle, it is happens when the state change from 4 to 1. This state 4, the temperature is the same as the state 3, and state 1, the temperature is the same as the state 2. And therefore, we know that the temperature of the state 4 is less than the temperature at the state 1. Then the temperature change when the state change from 4 to 1 is a positive value. And because this process is adiabatic compressions, we know that the Q value should take 0. That means there's no heat transfer happens in the gas. So Q equal to 0. We highlight here the relevant informations that require for us to plot the graph of temperature versus entropy. The entropy change is given as a Q versus T, where the T is a constant positive value in Kelvin. Therefore, we know that for the process of 1 to 2, since the Q is positive value, therefore the delta S should be positive value. Entropy increase in the first process, isothermal expansion. For the state, when the state change from 2 to 3, the Q is equal to 0. So based on this formula, we know that there is no change of the entropy. And for state 3 to 4, the Q is a negative value. Therefore, based on this formula, we know that this entropy change is less than 0. So in the state 3 to state 4 process, the entropy reduced. And from state 4 to state 1, since the Q is equal to 0, again by these definitions of the entropy change, then we have this entropy change equal to 0. For state 4 to 1, there is no entropy change. This is the final forms or final list of the informations that we need to plot the graph of temperature versus the entropy. Now we will start to plot the graph. For the process of state 1 change to state 2, the temperature is constant and the entropy is increased. So now if we start from a point here that represents the state 1, we should draw a line that extends to the right. This arrowhead indicates the directions of the process. The directions of the change of the entropy, which is increased to the state number 2. So that means we will get a horizontal line in the graph of T versus the S. The T is in Kelvin, the S is in joule per Kelvin. For state 2 to 3, temperature drop. That means we should draw a line that points downwards, going down, and the entropy change is 0. That means this happens, the entropy drop happens at the temperature drop happens at the entropy, constant entropy. So that means we will get a vertical line that points downwards. For state 3 to state 4, it happens at the constant temperature and the entropy is dropped. Therefore, we should draw a line that extends to the left. In the process of state 4 to state 1, the temperature increase whilst the entropy is constant. Therefore, we should have a line that points up vertically, and the state will go back to the original state, which is a state 1, and we'll get a closed loops, which is a cyclic process. In solving these questions, we should take notes that out of the 4 processes in the Carnot cycle, only these 2 processes, the entropy change is not equal to 0. For this process, state 1 change to state 2. This is isothermal expansions. The heat flow into the gas. Therefore, the entropy change is a positive value based on this formula. And from the state 3 to 4, this process, which is isothermal compressions, the entropy change is less than 0, because the heat is flowing away from the system or from the gas. So according to this formula, then delta S is less than 0. But the magnitude of this delta S, these 2 delta S, they are the same. Therefore, when we add up these 2, we will get the total entropy change for the complete cycle should be equal to 0. So that is why we know that why these 2 lines, when we sketch them, they must have the equal length, although points in the opposite directions. Because we know that this entropy change, entropy itself is the state function. When the state start from state number 1 and then go through the state 2, 3, and 4, and then finally come back to 1, the entropy change must be equal to 0, because entropy is a state function. Therefore, that's why we know the entropy change happen in this process, which is increasing, must be equal to the entropy change in this process, which is decreasing. So when we add up the total entropy change for this cyclic process, must be equal to 0. That's why we know that these 2 lengths must be equal. So now we completed our task of transforming the Carnot cycle represented in the P versus V graph into the graph of the T versus S.